Hey guys, this is lesson 3.2. So go ahead and try the warm-up. These are limits that we did in the beginning of calculus. So just a review of some limits. When you're ready, you can unpause. All right, so let's look at number 1. What we really want to do here is distribute out the 2 plus x to the third. Okay, so we're going to start by doing 2 plus x squared, so that would give me 4 plus 4x plus x squared, and then I'm going to multiply that by another 2 plus x. The minus 8 is still at the end. Okay, so this would give me, when I distribute out again, I'm going to get 8 plus 8x plus 2x squared plus 4x squared plus x cubed minus 8. Okay, so at this point, the 8's are going to cancel. And actually, one x can cancel off of everything. So this x is gone, that's a 1, that x is gone, that's a 1, that's a 2, and that's gone. Okay, so now I have 8 plus 2x plus 4 plus 4x plus x squared. X is 0, so the only things that are not going to disappear are the 8 and the 4, so this equals 12. All right, number 2. All right, on number 2, we actually have no problem plugging in the 1. So this is going to give me 1 squared times the natural log of 2 minus radical 1. So 2 minus radical 1 is 1. And the natural log of 1 is 0. So that gives me 0. All right, number 3, since it's going to infinity, we're going to divide everything by the highest power in the denominator, which is x. Okay, so we're going to do 2x over x, 3 over x, 5x over x, and 7 over x. So my x's are going to cancel here and here. Anytime you have an x in the denominator and x is going to infinity, those are going to become zeros. Okay, so this becomes 2/5. All right, number 4, I gave you a hint to factor. This is both difference of perfect squares. So in the top, we have x plus a, oops, I don't need an equal sign. X plus a, x minus a, and then in the denominator we have x squared plus a squared and x squared minus a squared. And actually I'm noticing if I didn't factor the top, I would just cancel that, x squared minus a squared, so I know that's this. So I'm going to cancel that. And then here I'm ready to go ahead and let my x become a. So this becomes 1 over a squared plus a squared, which is 1 over 2a squared. All right, so in today's lesson, we are going to look at Rolle's theorem and the mean value theorem. Let's start with Rolle's theorem. It says, suppose that y equal to f of x is continuous over the closed interval from a to b, and differentiable at every point on its interior, a to b. If f of a is equal to f of b, then there is at least one number c in that interval at which the derivative is equal to 0. Okay, so let me just show you what this means, because it does make sense when you really think about it. Okay, so I'm going to draw this up here. Okay, so this is saying I have f of a is equal to f of b. So that means at some point a and some point b, they have the same y value, okay? So I'm going to make that y value here, okay? And that means that all throughout this graph, this is just some graph. I'm just going to draw a very simple, maybe like a parabola. Oops. Okay. And so what this says is, look if I start out at a certain y value and I make my way back to that y value, at some point in time, my derivative had to be 0 because this had to loop back around. Okay, so that's where my derivative is 0 right there at that maximum point. And this is always going to be true. Okay, so let me give you maybe just one more different example. Let's say I had A here, B here. Again, they have the same y value. So let's say this graph did that. Well, then in this case, I would have a derivative of 0 here, and I kind of went off the screen a little bit, but they're at the top. Okay, and all of those would be 0. So let's show an example of how you might use this theorem. Okay, hopefully that makes sense to you. And now let's look at an example of how you might use that. It says, show that the equation x cubed plus 3x plus 1 equals 0 has exactly one solution. Okay, so the first thing we're going to do is we're going to prove it actually has a solution. And we're going to do that by the intermediate value theorem. Hopefully you remember that. So for the intermediate value theorem, we're just going to pick two x values. And what we want to do here is we want to get one x value that is less than 0 and one x value that is greater than 0. Because remember, since this is a continuous function, that means at some point it will hit 0. All right, so let's try, I'm going to call this f, even though, in fact, let me write that down. Let f of x equal this function. Okay. So how about I could pick -1. Okay, so this would give me -1 minus 3 plus 1, which is -3. Okay, and then let me try 0. That would give me 0 plus 0 plus 1, which is 1. Okay, so since we have a negative and a positive, at some point f of x is going to equal 0, okay? And that point is going to happen between -1 and 0. All right, you might want to write that out. I don't really have room, but maybe you could write f of x equals 0 at some point between -1 and 0. All right, so what we just proved is that there is a solution. We want to prove there's exactly one, okay? So what we're going to do now is we're going to use Rolle's theorem. So we're going to go ahead and take the derivative of f. Okay, so this would give me 3x squared plus 3. And I want to set it equal to 0. All right, when I set this equal to 0, let me factor out a 3. Okay, and I want you to look at this here. If you notice, this is supposed to be equal to 0. Since x is being squared, there is no value I would be able to put in that would give me a -1 for this to be equal to 0. So there is no real zeros here. Okay? So what that means is there's no point on this graph where it turns around. So think about our example at the top, okay? If we were gonna go back towards 0, it would have to at some point turn around, right? So since we've already proven there is a 0, and now we've proven that there's no tangent line that is 0, basically this graph cannot turn back around and hit 0 again, okay? All right, so let's write down for our explanation. Oh goodness, I have no room. All right, I'm gonna go down here and you can hopefully fit it on your paper. So I'm gonna write, if there was another 0 at some point, the derivative would be 0. So there is only one solution. Okay. Okay, the next theorem is the mean value theorem. It says, suppose y equal to f of x is continuous over a closed interval a to b and differentiable on the interval's interior a to b. Then there is at least one point C in AB at which f of b minus f of a over b minus a is equal to f prime of c. Okay, so hopefully, I am hoping that you guys, when you looked at this part of the theorem, notice that this is basically slope, right? This is the rate of change. And so this is saying that the rate of change, the slope between A and B, if we were just to make a straight line between A and B, and the slope of that line, there's some point along the graph that has the same slope of the tangent at that point. Okay, so let me just draw a picture down here. And I wrote here, note, it's not always easy to find C algebraically, even though we know it always exists. Okay, so let's draw a picture. Let me explain what mean value theorem means here. Okay, so we have, hang on, I'm going to go up a little bit so I have room. There we go. A and B. Okay, so this is just some graph here. Okay, here's A, here's B. And so what the mean value theorem says is if I just found the slope of this line between A and B, which would be f of b minus f of a, right? The change in the y's over the change in the x. So if I just found the slope of that, this theorem says there is a point on this graph that has the same tangent slope. Okay, so let me just draw that. And so this would be f prime of c, the same slope. And I guess then that would be my c right there. Okay. Okay, so let's look at an example. The function f of x equals x squared is continuous from 0 to 2 and differentiable for 0 to 2. Okay, so let's look at that. Here we have, let's see, f of 0 equals 0 squared, which is 0. F of 2 is 2 squared, which is 4. So the difference of the y's over the difference of the x's would give me 2. And so by the mean value theorem, at some point between 0 and 2, the tangent line has a slope of 2. Okay, so on this one, it's actually really easy to find it. So if we do the derivative, that's 2x. If we set that equal to 2, which is what we wanted the slope to be, we find that that point is at 1. Okay, I'm going to graph that just to show you. Okay, this is an easy one because we know this graph so well. So we have 0, 0, 2, 4, 2. Okay, so it looks like this. And so the slope between 0 and 2 is 2 here. Okay. The slope is 2. And then at this point 1 as well. This tangent is also 2, the slope of the tangent. Okay, let's look at the next page. Example 3. It took 14 seconds for a mercury thermometer to rise from negative 19 degrees Celsius to 100 degrees Celsius when it was taken from a freezer and placed in boiling water. show that somewhere along the way, the mercury was rising at the rate of 8.5 degrees Celsius per second. Okay, so on this one, if we look at the degrees per second, degrees per second. Okay, so let's just look at the average rate of change. It took 14 seconds, right, to go from 100 to negative 19. Well, negative 19 to 100, but I'm going to subtract the other way, so it's positive. Okay, so this gives me 119 over 14, which when you divide it is 8.5. So what this means is at some point it was rising at 8.5 degrees Celsius per second. So by the mean value theorem, at some time it was rising at 8.5 degrees Celsius per second. Okay, number 4, find the function with derivative y prime equals 1 over x squared plus 2x, whose graph passes through the point negative 1, 1. Okay, so this is a little bit different. It actually has nothing to do with the mean value theorem, so we're just going to do this problem. We're kind of leading towards antiderivatives, which you're kind of probably going to notice on this. So let's rewrite this as x to the negative 2 plus 2x. So our job here is to actually find an equation that would be a function that when I took its derivative, I would get this, okay? Okay, so I'm going to start with the second part, the 2x, okay? So I'm thinking to myself, okay, when I took this derivative, the 2 came down in front, right? So there was probably a 2 here. And then it was subtracted by 1 and it becomes a 1. So that would actually be just x squared, right? Because then when I do the 2, comes down in front, becomes a 1. Okay, that works out. The other one's a little bit trickier. So on the other one, well, first let's start with this. I know that 1 was minused from this to get to this point. So that means that originally it had to be a negative 1, right? Because when I did the derivative, I know I minused 1 from it and it became negative 2. Now that means that this negative 1 was multiplied into the front. So something had to be here so that when I multiplied it, I ended up with just a 1. So in this case, that would just be a negative 1, okay? Because what that would do is it would times become a positive 1, and then when I subtract 1 from the negative 1, I get the negative 2. All right, so that's nice, that's good. Now, the only thing left is, remember, when you do a derivative, like for instance, back here on this one, there was a 1 in this equation, right? And when I did the derivative, the 1 completely disappeared. So when I do this antiderivative, as I'm calling it here, there's a possibility that there was a constant on the end of this, that when I did the derivative, it went away. Okay, so we need that plus c. And that's actually where we're going to use this point right here. Okay, so what we're going to do now is we're going to take our function, we're going to plug in this point for x, y, and that is going to show us what our c was, our constant was in the original, okay? All right, so let's do that. Over here, so the y is 1, the x is negative 1. Plus c. Okay. All right, so let's work on this negative 1 to the negative 1. I'm going to rewrite it as a fraction. negative 1 over negative 1, right? Okay, so here's my negative 1 on the top, my negative 1 on the bottom, right? Negative 1 squared is 1. Okay, so this would become 1 plus 1, so 2. So when I minus the 2, I get negative 1. All right, so my final answer is y equals negative x to the negative 1 plus x squared minus 1. There we go.